So with that, join me in welcoming our speaker, and I'll turn it over to you, Robert.
Hi, everybody. Are my slides progressing?
Yes, they
All
look
right,
good.
we're good. Outstanding. Okay. So my name is Robert Hayes. I was in industry for about 15 years before I came over to academia. When I came into academia, I brought with me basically my experience where I put together a program here at North Carolina State University, an undergraduate minor in health physics and a graduate certificate in health physics, which is basically code for radiation protection or radiological safety. So I teach a lot of courses in that. I do a lot of research in that. These are some of the toys down here in my laboratory: electron paramagnetic resonance and thermoluminescence and optically stimulated luminescence. But that's not what I'm talking about today. I'm talking about public trust in basically nuclear science, specifically the science of radiation safety and radiological protection. You're going to see there's a lot of misinformation out there about that. And so that's what we're going to talk about, the myths versus the facts. So here's the outline. We're going to be talking, I need to start off with fission. There's some context there. And then we're going to go right into it. Radiation risk and context. What is the risk from different doses? That's probably the biggest part right there, is not knowing what risks are from different doses. What is a dose? What's a milligram? What's a gray? If you don't know these things, it's hard to contextualize it. But then we'll look at the rest of the things in the industry and in society that terrify people. Nuclear waste, environmental impact, nuclear accidents. Those can be very scary, but we need to get the context. What is the actual radiological risk? That's really all we're talking about, is radiological risk. So fission, hopefully everybody already understands the concept of splitting a bunch of uranium nuclei. Uranium-235 is going to give rise to these fission products. What's of interest, and it's going to give a lot of context further on, is that when you fission a uranium atom, you get about 200 mega electron volts of energy out of that, as opposed to fossil fuels, where you get about an electron volt per atom that's taking place in that process. Now, the distribution of these fission products that come out are centered around two different mass values. This is going to be significant later. There's basically a signature of the distribution. So you can get a lot of different fission products that will come out of a fission event, but they tend to have a distribution. And we'll talk about that when it comes to nuclear waste later. But that's important to remember, is that there are isotopic signatures that are associated with fission. Now, here's the fuel cycle, and there are different aspects that are going to scare different people, but we'll just walk through it real quick. To start off with, when you're doing, we get the uranium from the ground. You do just like any other metal. Historically, you dig a hole and then you mill it, and then you refine it. With uranium, once we've gotten the milling process is done, then there's a chemical conversion to uranium hexafluoride. So we don't turn it into a metal directly. You want that uranium hexafluoride because that allows us to do the enrichment. Basically, the uranium-235, it's only about 0.7%. So we've got to enrich that with a centrifuge process to get it up to about 5%, at which point then we make it into fuel, little pellets. And once it's in pellets, then we'll turn it into fuel rods and bundles that go into a nuclear power plant. It keeps advancing. I apologize. My trackpad is advancing when I don't want it to. Then we burn it in a nuclear power plant, get a lot of fission energy out of it, make a bunch of heat, boil water, make steam, turn a turbine, make electricity. And right now, then it goes into interim storage. Now, right now, the goal is that it would be going into a geological repository. But as far as I know, every nuclear scientist I've ever met, the ideal would be to recycle it. And then you have a closed fuel cycle so that you're not only getting about 5% of the energy, which is all that we get right now with an open fuel cycle. But if we recycled it, we could get a lot more energy for all the mining and milling that we do. All right, now we can talk about radiation risk. So let's start off with something that will allow us to visualize everything else. We're going to use US units because that's what the regulations are still written in here in the United States. A millirem, that's approximately 1 daily background. This is on average. It's a little it's a little bit lower than that. That's a good approximation. You get about a millirem per day just because you're living and breathing and walking around, breathing in natural radon, getting natural cosmic radiation, just the radiation that you get because you're alive. In the United States, it's higher in other places, but in the United States, that's about what it is. 5 milligram. That's about the dose you get for a coast-to-coast trip from LA to New York. There and back again, you get about 5 milligram. That's also the drinking water standard. Now, this is where you can start to see fear takes place. You're not afraid of a dose from a coast-to-coast trip on a plane, but you would be afraid to find out that your drinking water can give you a higher dose than the EPA would say is allowable by regulation. So that's where you start to see there's something that seems to be a little bit different about what you would expect based on where you would think the regulations would be. 10 milligram, that's the offsite dose limit for effluent from a nuclear facility to the nearest resident. 10 milligram per year is the maximum dose you can get offsite. Now, to contextualize that, that's the minimum dose that you have to get to be a healthy human being due to the necessity of having potassium. Potassium and sodium, they're essential to life, and you have to have a balance. And if you don't have enough potassium, that can be a serious health risk. You got to have potassium. The potassium sodium pump is what gets water in and out of cells and keeps that trigger pressure. And 10 milligram, that's that minimum offsite limit. You've got to be below that to be meeting the regulations. 40 milligram. Potassium, it scales with muscle content. So if you're a large muscular male, you can get up to 40 milligram a year due to internal potassium. 10 milligram, that's like a small petite female or a child. If you don't have a lot of muscle, then you're going to get a lower dose. So again, this is contextualizing the magnitude of these doses that we're looking at. This is going to be a logarithmic scale. We're going to go logarithmic through here. So we're not going to go a linear scale. This is going to be logarithmic. 100 milligram. That's about the dose you get for a pelvic x-ray. So if anybody's broke a hip and you just got an x-ray, that's about 100 milligram. That's also the public limit to a nuclear facility. So if I was walking up to a fence at a nuclear power plant, the maximum dose I could get for living there for an entire year is 100 milligram. So that's the maximum it can be at a fence, 100 milligram per year. 320 milligram. All right, this is the average natural radiation dose to a US citizen. We're going to see there's a lot of variation there, but if you average out based on the population centers, it's about 320 milligram per year, which is why 1 milligram is approximately your daily dose just because you're living and breathing. 320 milligram, that's your average natural background dose. Going orders of magnitude again, 1,000 milligram. For those of you that are old like me, you've had a heart scan where you've been injected with radioactive thallium to do a stress test, and that's about 1,000 milligram dose. It's also about the dose you get for a CT scan to the head. I've had one of those, to the chest or torso. 1,000 milligram, that's about the dose you get from those medical procedures. It's also the minimum dose that a member of the public would have to get before the EPA could issue evacuation orders to a governor if there was a nuclear event. So again, you start seeing how all of these things, if you don't understand the dose, but you're getting these regulations and emergency evacuation, that can be terrifying. That can be petrifying to think that I'm just moving because I'm avoiding the dose that I would get from my CT scan I had last week. There's a lot of cognitive dissonance that can start to take place if you don't understand radiological risk in context. The actual limit in the United States is probably going to be about 2 rem per year the first year, and then a half a rem per year after that. So if you can get 2 rem the first year and then half a rem per year after that from a nuclear event, then the EPA will likely issue evacuation recommendations to a governor, and you get an exclusion zone. 5,000 milligram. That's a legal dose to a radiation worker in the United States. This is considered, if there is such a thing, if linear no threshold is true and all radiation comes with increased cancer risk, then 5,000 milligram is consistent with safe worker standards, so that you can get up to 5,000 milligram per year if you're a radiation worker. If you're properly trained, you know how to protect yourself, you know how to interpret measurements, and you understand the basic concepts of radiological risk, you can get up to 5,000 milligram per year legally in the United States. Again, going up logarithmically here all the way through. 10,000 milligram, we finally hit a threshold. 10,000 milligram, there's one journal paper that shows that you can get a 0.5% cancer increase. This is only for children. 0.5% cancer increase over natural probability. Now, your natural probability, if you live long enough, of averaged over all genders in the United States, is about 40%. So if you live long enough, you got a 40% chance of getting cancer if you don't die from something else before that. And so 0.5% is pretty small, but we finally hit a threshold where there is actual good science to show that you get some kind of cancer probability. Going up to 1,000 milligram, or sorry, 100,000 milligram. That's a 5% cancer probability. That's good science. We have good solid evidence to show that if you get 100,000 milligram, your cancer probability is going to increase by 5% over the natural incident. 500,000 milligram. All right, this is what we call a lethal exposure. This is the LD 5030. This means that if you've got 500,000 milligram, 50% of the population will die within 30 days if you don't get medical treatment. Now, we know this from the atomic bomb survivors. If you do get medical treatment, then your chance of survival goes up a lot more. But this is acute radiation syndrome, and this is not cancer. This is radiation sickness. And then by the time you get up to 1,000,000 milligram, now we're looking at hospice. This is basically central nervous system failure. And so to put it in context, everything up here in the green are regulatory limits where there are no measurable medical effects expected. Nothing, if there are medical effects, they're too small to see. Everything down below, that's where there is good science to show that. And everything up in the green is in the regulatory space. That's where regulations are, that's where we can basically control radiation with quality. In the nuclear industry, radiation dose is considered like waste. You just minimize your waste. It doesn't mean that if you had some waste that's bad. Everything has waste, but the principle is that you simply minimize the waste. And if you can do it with quality and with control, then that's about where those limits are. And unless you understand these limits, it's easy to get terrified, right? Because before you saw this, how many people would have actually known what a milligram is, right? That could be terrifying. And it has terrified people. And we'll see instances where that 1 milligram has literally scared people to the point of panic, that 1 milligram. So let's keep going. Use nuclear fuel. This one can scare a lot of people. And what is it? It's these large casks that have used nuclear fuel in them. And they're quite large. And when you look at them, if you see these fences, when you look around them, when you see those fences, remember that's 100 milligram per year limit. So if a cowboy went and pitched a tent right there, the maximum dose they could get is 100 milligram, which is a fraction of natural background. And that's the level of radiation that you get from these facilities. And yet they terrify people. So this is what those fuel pellets look like. They go into these zirconium cylindrical rods, and then they go into these fuel assemblies. And then once they're burned in a reactor, then those are what go into these casks. And here you see some technicians doing regular monitoring. And these are those casks that would store used nuclear fuel. Now, if you wanted to scare people, you would talk about how many pounds this is, because there's a lot, this stuff is very dense. And that can scare people because you're going to get millions of pounds, and that can sound like an awful lot. But let's contextualize this. In about the past 50 years, the United States has got about 20% of its electricity from nuclear energy. Now, for the largest economy on the planet, a manufacturing powerhouse like the United States, 20% of our electricity for 50 years is an awful lot of electricity. And all of that electricity, for all of the spent fuel that's been created from that, it would not fill up a single football field above 10 meters high. These casks that you see there, they would not even fill up a single football field. That's how small it is. It's just, and that's what we started with at the beginning, is the energy density difference between nuclear and fossil fuels, right? We're talking hundreds of millions of times higher energy density in nuclear than you have with fossil fuels. And if you have a high energy density, you have low waste. You just don't need a lot of materials if you got a massive energy density. That's why we like fusion. It's a high energy density. Well, these things scare people, right? Transporting these things, because these are supposed to go on rails through across the country. Well, how indestructible are they? They are not indestructible, but they are pretty close. And this is why you can say that. This is the criteria, the legal criteria in order to get a license to build these. It's got to go through this testing criteria through the NRC. It's got to do a 30-foot drop onto its weakest point. So you do a finite element analysis of the cask, and you find out what is the weakest point on that cask. It's got to do a 30-foot drop into an unyielding surface. Wham! And it can't leak. That same cask then has to do a 40-inch drop onto a steel bar. Wham! Again, the weakest point. Then it's got to go for a half an hour at almost 1,500 degrees Fahrenheit and not leak. And then it's got to go 50 foot underwater for 8 hours and not leak. The idea is that this is the worst hypothetical accident scenario you could have. The casket rolls off a cliff, wham, 30 foot onto a rock. And then it falls onto a pointed rock, slam onto that pointed rock. But then it's in a tunnel fire and it's got to sit there and burn. And then as they put it out, it rolls into a lake. And if it can do all of these sequentially without leaking, no detectable leaks, then you can get a license to build them. So they are destructible, but they would be very, very difficult to destroy. And so they're very big and they're very expensive. Well, what about the waste? What about a solution for the waste? A lot of people like to point out that we don't have a solution for the waste. Well, in southeast New Mexico, there is a licensed geological repository for transuranic waste, basically plutonium contaminated waste. And it's called the Waste Isolation Pilot Plant. And it's in a formation that's about a mile thick of water evaporites. And the cross-sectional area of this formation is comparable to many Western states. It's an enormous salt formation. Now, here on the left, it's a cute photo. This gentleman is a miner. He's a licensed miner. And he's operating this miner here, this big thing up with a belly box. It's a remote controlled miner. So it's a miner operating a miner, digging through the salt. And I think that's just a fun photo to show how easy it is to mine this salt. And on the right here, you have a schematic of the stratigraphy. Now, the upper half is almost pure sodium chloride, and then below it, there are layers of calcium sulfate and sodium chloride, basically water evaporites from an ancient seabed. And right there at the WIP level, it's about 200 million years old. And so this is just incredibly stable geology. This stuff is elastoplastic. It moves in such a way as there are no fault lines there. It just simply moves if there is any kind of a stress or strain. It just simply accommodates it. The crystal grains will slide on each other's surface. And so it's incredibly stable, and there's no water movement that's going to be comparable to anything that would cause any advective transport in a substantive way, because it's just incredibly stable geology. Now, while I was working there, this happened. These on the left, you see the actual waste containers. They're a bunch of 55-gallon drums and some 10 drum overpacks. And this is what the waste is transported in. On top of those, you see magnesium oxide a buffer to keep the chemistry at an ambient level. And one of these drums deflagrated. It basically exploded. And that's what you see on the right. On the right is the trace that was left from that. You see this green blob? That would terrify people. They think, oh my goodness, a transuranic waste geological repository had a drum explode and it gave rise to this release. Now, the stuff that was released was americium-241. It's a transuranic radionuclide. And when this occurred, all of the safety features worked as designed. And this release was basically the maximum release that you could expect from that kind of an event. And you can see why it's terrifying. This green glob there, all right? The analysis was done there on the lower left. I did that analysis. And to put this in context, the americium that was deposited on the ground there was comparable to the americium that was there from atmospheric weapons testing in the prior century. So what was done in the late 1900s from americium that was all over the United States was basically about what you got there in that green glob. And that terrified people. But again, without context, it's just scary to many people. And so this is just trying to help contextualize this. A lot of people will say, well, who's going to be around in a million years to make sure this is safe? How do you know that it's going to be safe in a million years? How do you know geology is right? How do you know that geology can predict what's going to happen geologically if we bury this stuff like at the WIP site? How do you know what's going to happen? And the quintessential example occurred at Oklo, Gabon. Now, I mentioned earlier that the uranium-235, the fissile component, what you actually have to enrich up to 5% from the 0.7% that it occurs naturally, that has a much shorter half-life than the dominant isotope, uranium-238. Uranium-238 has a half-life that's about the age of the Earth, about 4.5 billion years. The uranium-235, the fissile component, has a half-life that's just over 700 million years. So it's got a much shorter half-life. That means that the uranium-235 has been decaying exponentially faster than the uranium-238. But if you go back a couple billion years, then the natural enrichment of uranium is going to be about 5%, basically what we have in commercial nuclear fuel. And this was discovered in Oklo, Gabon. You can see the little cutout there of where it's at in Africa, where there was a uranium mine. And when they went and did the enrichment for this, they found that they weren't getting the enrichment that they expected. They should have had commercial nuclear fuel, and it was a little bit lower. And so they had to ask, well, what's going on? What would cause this? And the funny thing is that when they looked at the isotopics of the other rare earth elements and the metals that were there, they were completely out of whack. And here's an example over here on the right. You can see the isotopic distribution of natural neodymium. Now, neodymium, it's got 60 protons, but it's got a different distribution of neutrons that are present that will give you the atomic mass down here. So the average atomic mass is 144.23. But that's because it's a mix of all of these other isotopes, different amounts of neutrons that are stable. And this histogram here on the top left shows you what you get basically anywhere else on the planet that we've seen it. Now, if you look on the bottom left, you see the neodymium the isotopics of the neodymium from Oklo are completely different. They're completely different than anywhere else that you've seen on the planet. And the funny thing is that if you do a superposition of neodymium from uranium-235 fission with that of natural neodymium, you basically reproduce the neodymium from the Oklo mine to within statistical significance. So that if you do a correction, you can see that the neodymium from Oklo, after you subtract out the natural distribution, is indistinguishable from fission. And this is what we saw with all the other terminal fission products, is that the isotopic distribution was a fingerprint for fission, meaning literally, and I did some research on this as well, down at the bottom, that's my reference, meaning that you literally can say that Mother Nature made her own natural nuclear fission reactor, and she disposed of that spent nuclear fuel in the ground in such a safe way that it stayed there until it literally just became a different kind of dirt. That was it. It just became a different kind of dirt. But it comes down to geology, having good geology. And as long as you got good geology, then, geology is good. We like geology. And geology can help us in a lot of different ways. Well, where do we get all these different doses? So I was quoting a bunch of doses earlier, and a lot of them come from medicine, but there are a lot of natural ones as well. Radon is a big one. Now, the one that really scares people generally is going to be nuclear energy. That tends to be the one that scares most people when it comes to radiation exposure. And if we look at what are the fractions of all of these, you can see that when it comes to natural is here on the left, or on the right, sorry. On the green are all the natural exposure. And you can see the biggest chunk of natural radiation exposure is radon, the air you breathe. You might not have known this, but every breath of air that you've ever taken has been radioactive. Likewise, every morsel of food you've ever eaten has been radioactive. It's got potassium, which is naturally radioactive. But because of the power and the utility of nuclear medicine and radiography, that's about comparable. And when you average it out, mostly it's older folk like me that get these exposures from different kinds of treatments. But we get about the same amount. This is averaging over US citizens, about the same amount from medicine as we get from natural. And if you look up here, this tiny little sliver up at the top, industrial, that includes things like industrial radiography and medical sterilization and other applications, but it also includes nuclear energy. And you can see it's just a tiny sliver. And that's the one that terrifies people, not any of these bigger ones, right? Because of the medical benefit that we get from nuclear medicine, or the fact that, you're not going to filter radon out from the air unless you're in your home. You're not going to do anything about the outdoors. That doesn't scare us. But the one about nuclear energy, that tends to scare a lot of people. Here's the distribution. And you can see that where the doses are going to be higher, you don't have as much population. In the top left is the potassium concentrations. This is from the United States Geological Survey. You can see where it's red, it gets quite high. The bottom left is the thorium concentrations. The bottom right is uranium. And then the top right is cosmic. And you can see it's the Colorado Plateau. That's where you get the biggest chunk. So that fresh mountain air, it's going to have higher concentrations of radon. Same with the water that's coming down there. The granite tends to concentrate uranium. So the granite countertops are going to be a larger source of radon than you would get for something that's something like basalt, simply due to the uranium content that's going to be in that granite or the rock that you're using. Environmental impact. So let's talk about that. That a lot of people are under the impression that nuclear energy has the potential for a substantially larger environmental impact. Armageddon, Hollywood is a good example of this. There's a lot of movies where you get environmental impact just from nuclear energy. Let's talk about that. Well, why are renewables so important? It's because of greenhouse gases. And that's why nuclear is also important from an environmental perspective, is because it has very low greenhouse gases. Now, I specifically picked this graph. There, basically almost any graph you pull up, it will look at life cycle greenhouse gas emissions, will show you that nuclear is as low or lower than traditional renewables. But what's interesting is that geothermal is placed as renewable here. And I specifically like that because geothermal, the majority of geothermal energy comes from the radioactive decay of the potassium and the uranium and thoriums and their decay products. I showed you that graph of the distribution just in the United States. And if you distribute that throughout the planet, all of that radioactive decay creates heat. And remembering the laws of physics, the temperature is going to increase for a heat source until the heat extraction rate is equal to the heat generation rate. And once you get into an equilibrium, that determines what that temperature is going to be. And so most geothermal is actually radioactive decay of the primordial radionuclides. That's just an interesting aside. Materials, that's a big deal, right? Mining and milling and manufacturing, all of the factories. If you don't look at the fuel, but you only look at what it takes to generate a terawatt hour of energy, then traditional renewables are going to have a massive impact in terms of all the mines, right? I don't want to have 10 times the number of mines to get the same amount of energy. I'd like to have a lot less. And if you go with either fossil fuels or nuclear, you get a lot less. The problem with fossil fuels, we all know, is that they create climate change, which is why nuclear also is attractive for climate considerations. Now, here's an interesting one, the land use. So if I'm looking at deployment, this is a logarithmic scale or semi-log vertically. You see that nuclear has the smallest footprint. And this is the same reason why we like fusion. It's just a high energy density, so it's got a small footprint. Now, you see on this graph that photovoltaics, it's over 100 times more if I'm doing traditional solar. And the problem with that is that that's traditional solar. If we were to put solar, say, on rooftops or over roads, this would go down drastically. But because we don't tend to do that, it ends up being like this on the graph. And until we start actually using useless land to deploy our photovoltaics, it's going to still end up on a graph like that. So hopefully that'll change. All right. This is a big one for a lot of people. When you talk about nuclear energy, some people will just say 3 Mile Island or Fukushima or Chernobyl or any combination and think that that ends the conversation. So let's look at these in context. Now that we have some ideas to what radiological risk is, let's go ahead and look at these accidents. So 3 Mile Island. The reason I picked the 1 millirem to start off with that logarithmic scale was because the average dose to the member of the public from 3 Mile Island was 1 millirem. And remember, I told you that's the smallest one we looked at, and that terrifies people. And that's what happened at 3 Mile Island. Because who knows what a millirem is, right? Somebody says, it's only a millirem. Well, what's a millirem? I don't know. Is that going to kill me? Right? That potentially is a reason for panic if you don't know. And so, yes, it was very bad, but mainly from a cost and a fear. It terrified people, and it cost a lot of money. And so it was a big deal, but it wasn't enough of a radiological risk to cause any concern at all. In fact, daily variations are generally going to be large compared to that if you're living in a place like the Colorado Plateau. And if you go indoors and there's no radon mitigation, it can be a lot higher. So just daily variations can be large compared to that or comparable to just that dose. And yet it terrified people. Well, what about Fukushima? Right? That was a Western design. Now, remember, I pointed out that the threshold for evacuation is comparable to, say, a CT scan to the hip or to a head, or a stress test where you do a heart scan. The maximum dose to the members of the public in Japan was less than 1,000 millirem, because they evacuated, and they, even if they had done it longer, it still wouldn't have gotten above that 2,000 millirem threshold. And so if you look at either what the United Nations said, I referenced it there, the World Health Organization, or any of the review papers, the astonishing thing is that because of all of the radiation that was released, it was insufficient to produce expected measurable medical effects in the Japanese public ever. ever. Now that should just slap some people in the face hard, to think that the Japanese event was horrific. It was the only people that died from that were in the panicked evacuation. So they died trying to avoid a dose that would not have produced any measurable effects. That's the level of fear that you have with nuclear. And it's palatable, it's visceral, and yet it's real. And that happens in society. Now let's look at Chernobyl. Chernobyl, clearly, that was a horrible design. It was a horrible operation. And then it was a horrible emergency response, because you really didn't have any emergency response. If you'd have done any one of those three things right, it would have been closer to Fukushima. If you'd have done any one of those three things right, but they didn't. And so as a result, there are thousands of cancers, mostly children, even, and many of them were treatable. But yes, that's what happened. And they could have avoided most of that if they'd have just told people, don't drink the milk. Let's do a controlled evacuation, or shelter in place until the plume goes by. But they didn't. But here's the shocker. This is the one that just reeled me. This one shocked me as a health physicist when I learned this. And there's this study by Rehu and Rehu. Now, they came up with an initial study back in 2016 where they looked at a cohort of Estonian liquidators. These are the people that were part of the Soviet Union at the time, and they responded to Chernobyl. And so they knew who the people that responded were and the people who didn't. Basically, you had a perfect, or a rather idyllic epidemiological opportunity to say, here are the people that were exposed to Chernobyl, and here are the people that weren't, and they basically have identical lifestyles and everything else because they're from the same country. And in 2016, they couldn't find any statistically significant changes in cancer rates. But when they went back and looked at it in this paper, which I'm citing down here below, they did see finally a small statistically significant increase in cancer incidence for the liquidator responders. And what was shocking is that in both studies, what they found was a skyrocketing suicide rate. People were so afraid of Chernobyl that they lived in a state of stress, in a state of fear, and that they had a tendency to attribute any medical effects that they had. If they had arthritis, that they had a wart, if they had any medical effect that was less than desirable, you could attribute it to Chernobyl. I mean, how do you know? How do you know Chernobyl didn't do that? And so anytime they had any kind of a medical problem, they blame Chernobyl. And so it becomes a self-fulfilling prophecy. And when you have no hope, you're simply more likely to commit suicide. And that's what they attributed it to, is this stigma, right? Ooh, you're exposed to Chernobyl. Ooh, are you going to grow a third arm? Are you going to get a third eye? Are your children going to become mutants? And so forth and so on. And so that was the biggest effect of all, and it was based on fear. Another fear that people have when it comes to nuclear energy is the danger that comes from terrorists or war. And an interesting fact is that even before 9/11, by law, a nuclear power plant had to withstand a large jet impact head on and no release. And so that's how it was designed. So, I mean, that doesn't mean that it's impregnable or that that it's indestructible. It just means it's incredibly robust. It's like those transportation containers. They are incredibly robust, but they're not indestructible. If you kept bombing one, eventually you would breach it for sure. Here's another one that's kind of surprising. General safety. So the bottom right is a study that was done where, again, with the United Nations, UNSCEAR, if you say that I'm not going to include Chernobyl with nuclear energy statistics, nuclear energy becomes substantially safer than anything else. It's only when you fold in, because again, remember, nobody in Fukushima died from radiation. In fact, there are no expected measurable medical effects to the Japanese public from the radiation ever. And so it's incredibly safe. When you think that's the worst that could happen, is that nobody in the public gets hurt, that's crazy safe. That is just insanely safe. But if you do include Chernobyl, if you say, no, we have to include Chernobyl with statistics, then you get the graph here on the left, where you see that nuclear is still safer than wind in terms of the number of deaths from accidents caused by enjoying that energy. And another funny thing is that the hydropower, if you look at that, you can see hydropower, that also includes the Bengqiao Dam, again, in the late 1900s in China. That went out, that took out a couple 100,000 people. You might say, well, that's not representative. Then yeah, okay, fine. In the United States, hydropower is crazy safe. Same with nuclear, it's crazy safe. But when you fold in all of these other incidents from around the world, then you get statistics that look like that. And so that brings me to the end where I can now answer questions if there are any questions.